So far we've talked about the auto-recurrence, so we're looking at one time series. Well, we have two axes, right, on the matrix, so why not use two time series? This is actually what I already talked about, but a little bit for the auto-recurrence, but it becomes now very important if you are looking at, for instance, if you within one person have measured two variables and you want to do a cross-recurrence analysis of that, and these variables are on different scales, it is of course important to adjust the scale before you do the state space reconstruction if you want to do that. Because you want to make sure that the two variables are at least on the same scale. And the least intrusive scale transformation is just the unit scale. So make sure that all the values are somewhere in between 0 and 1. And this is necessary because you're going to look at distances. So, right, if you've measured one thing in milliseconds and another thing in beats per minute or something like that, yeah, you might want to bring them to the same scale. I think the mean distance is less used for cross recurrence, but it is possible. Oh yeah, another thing. Yeah, when physicists talk about standard deviation, they talk about really the standard deviation and not the adjustment that we always use in statistics for population estimates, for estimates of population parameters. So in COSNET you can indicate whether you want to adjust I think it's called the n-1 adjustment, right? It's like the Bessel adjustment, I don't know. But at least you can get the unadjusted standard deviation also in COSNET. That means just dividing by n and not by n-1. Because that only makes sense in a statistical inference setting. Right, but the rest is all the same for cross-recurrence. So the idea is we are going to reconstruct again this state space, that at least if we're working with continuous data. I'll show you also categorical data examples. And then what happens if you do this and have two different time series on these axes of this matrix? So what you're doing is you're calculating actually the distance between the trajectories traversed by two different time series in the same state space. So the recurrent points then become, do at some point in time these two trajectories overlap, right? So are they synchronizing? Are they doing the same thing at some point in time? So this analysis, the cross-recurrence analysis, is used very often to study synchronization behavior. Now, an intuitive notion of synchronization you might get by looking at cross-correlations. So, for example, here I have a time series, and this is another time series, and it's actually exactly the same thing. I just shifted it 10 time points into the future and made this just 0. So this thing is repeating exactly after 10 time points. So if you would do a cross correlation, which you could also do in COSNET and Jamovi, we would expect here, at lag 10 we have a perfect correlation, almost perfect, of 1. So it's not exactly 1 because of the zeros. But that's by construction, right? So that's you could say, after a lag of 10, I have to wait 10 seconds, 10 days, 10 years, whatever you're looking at, and then I will find an exactly repeating pattern there. If you calculate cross correlations for instance, sine waves, I'm assuming that this is a sine wave. You usually get these kinds of patterns, and then very often the lag is also displayed negatively, so you can also sort of evaluate whether one time series is sort of lagging or preceding the other one. That's what this negative value then would mean. But again, when we're going to do the reconstruction for the state space in Cross-RQA, we're going to use the mutual information function. And interestingly, of course, you can use this to get because it's called mutual information, you can get an idea about how much information is shared in each time series at a specific lag. So it will often look a little bit different, this function, but still we will look at a first global minimum, or maybe a first local minimum, or a global minimum, and a maximum lag. But as you've seen already a little bit, it doesn't really matter which one you choose, just choose a value that's a little bit sensible. All right, so let's do this reconstruction based on one dimension of the Lorentz system, so the x dimension, which we already saw, and a spiral. So this is just a sine wave actually that is sort of spiraling down, and yeah, we could check whether this x dimension from the Lorentz system is actually synchronizing with this spiral behavior. Hi. Ah, okay. I had a nice picture about that. But, so if you do this reconstruction, of course, for the Lorentz system, we already know that you get the same values. You get dimension 3, and in this case, I think we chose a different delay. And for this spiral, for this sine wave, because we're using the same number of dimensions. This is also is dimension 3. So you now have to imagine that one of these time series is plotted below here, and one of them is plotted here. And what we're looking at right now is the distances that exist between the spiral and the reconstructed Lorentz series. And as you can see, it's actually, so the Lorentz is actually behaving probably pretty much like a sort of spiral. You can see that these oscillations sort of follow the sine wave, and here it goes off a little bit, but then it drops back into this same pattern again. So determinism here now means, so you can only calculate this, of course, after you've done the thresholding, but determinism here now means how many of the recurrent points in this plot are actually can be considered as trajectories that are shared at some point by these two different time series, by these two different state spaces, and so both it's pretty high. So it means, yeah, they are doing pretty much the same thing in this shared state space. Well, what you can see, of course, also is that the plot is now no longer symmetrical, right? We don't have a symmetrical plot here. There's a difference. So you can imagine there is a line here somewhere, but it does not pop up as neatly as the other examples that we showed with auto-recurrence. And so now it also becomes important to realize what is on which axis here. So what is on the y-axis and what is on the x-axis, because the number of vertical lines and the number of horizontal lines in a cross-recurrent plot will now be different. You can imagine that horizontal lines will be many more horizontal lines, especially in this region, than there are vertical lines. And yeah, this can actually give you some information about the type of joint dynamics that are going on But I will show you this in the categorical version of the RQA, because it's a little bit easier to explain that. Okay, so but this large piece here is of course related to this shared dynamics here, where you can see that sort of the sine wave is sort of coming in and out of the Lorentz system that is sort of constant in that period. And that's actually what's causing these nice little circles here. Okay, so this is just to very quickly show you, that's essentially you're doing the same thing, you're doing the same type of estimation. So the only difference would be that you can decide on the lag, on the joint lag, basically, by doing mutual information for both at the same time. But you could also do it separately and then take kind of a median or an average of these things. And the dimension estimation, you have to do it separately for each reconstruction. And you would always take the highest dimension, you get the highest result, because it's not. So it is important to get the right number, but it's not. So you can embed a time series in more than is recommended, more dimensions than is recommended, but it's not recommended to use too few dimensions to embed it. So usually take the highest result of this false nearest neighbor analysis. Okay. What else? Yeah. How real is this coupling? Well, again, you could do the shuffle, right? You could shuffle one of these time series and then do the reconstruction again. And then look at what's happening. So you don't do both, right? Usually in cross-recurrence, but you just take one axis and shuffle it and do the calculations again, and then figure out, are they still sharing a lot of trajectories in state space? Is this still the same? I would look something like this, for instance, if here you have the Lorentz system, and then this was the sine wave here, but now I've shuffled it all, and yeah, I can do again calculate what is the distance between all these points, and plot it as a recurrence plot. You see something like this. And of course, what has happened? Well, the determinism has dropped a lot, and linearity also. So probably our observed coupling here was at least not by coincidence, because if we shuffle one of them, we do not actually find the same measures here. So let me check if I am. Yeah. It's pretty much the same idea, but some of the measures are getting a different interpretation. So determinism means, so basically when a point is recurring, this means, yeah, there is a shared trajectory in state space by these two different reconstructed systems. So let's look at some applications, because that maybe hopefully will give you an idea how to use this. So the coupling of postural sway through communication, and then these will be more. This will be like continuous, and this will be more categorical examples. So this is a study, or a series of studies actually, which was done by Kevin Shockley, and Kevin Shockley was a PhD student of Michael Turvey, one of the famous ecological psychologists, and well, Michael Turvey always sends his students out to people from other disciplines who are doing interesting things, and so Shockley was sent to the people who invented, the physicists who invented recurrence quantification analysis, and yeah. The assignment was always bring back something that we can use in behavioral science or in ecological psychology. And so actually the first publication by Kevin Shockley, which was in 2002, is the first mention of cross-recurrence quantification analysis. So he actually went there and came back with cross-recurrence quantification analysis. It was a new way of using recurrence analysis. Yeah, so actually behavioral science had some input there. But that was of course a physics experiment, and then they quickly started to think about how can we use this in behavioral science. So what is the setup here? We have two people who are standing on a force plate, so we can measure the postural sway, right? If you're standing still, you're always moving a little bit, and by standing on they had a very expensive force plate. When we do this, we use the Wii balance boards, which give you the same results, or at least it's almost as accurate as those very expensive things, and much more portable. But they had two people come into the lab, and they had an assignment because they had to solve a puzzle by talking to each other. And the puzzle was, it's like a search for the differences, right? It's like you have these two pictures, and one is different from the other. And one person had just one version, and the other one had the one that was different, and they had to communicate and figure out what the differences were. And then there were different conditions. What they manipulated was the level of direct communication. So they could either be talking directly to one another. Of course, they could not see each other's puzzle, but they could see each other, right? They could be talking not directly to one another, but through a confederate. So they first had to say, okay, ask him this, and then the other one would. Confederate would relay this, and they would be actually talking through other people. And then they had a condition in which they could not see each other, but could talk to each other directly. And they had a condition where they could not see each other and also had to talk through confederates of the experiment. And well, what did they want to measure, or what did they want to study? It is known that if you're standing together and you can see each other, or you can have some kind of interaction, the postural sways will synchronize. So you will, at least most normal people will do this. And this happens automatically. It's just something that people do. Also, if you look at heart rate, that's always what I find very amazing. But if you put two people and have them interact with one another, you will see heart rates also synchronize. At least the dynamics of the heart rate variability. So that's something that they try to also manipulate here. So the question was actually, so in which condition will they most optimally synchronize? Yeah, what do you think? Do you have any expectations? You already have the slides, so you actually can skip ahead. So it turns out, so what you see here is they looked at mean percent of recurrence and the mean line. What is it? Oh yeah, so the mean here means that they aggregated over participants, of course. They looked at the max line from the recurrence analysis of the postural sways, right? So recurrent points, it's cross-recurrence, means more recurrent points means more synchronization. And max line means, it's referring to the maximum diagonal line, means the synchronization lasted for a longer time if the max line is high. But you can see that the body orientation, away or facing, and then the color indicates whether they could talk to a confederate or to a participant. The body orientation actually doesn't matter a lot. So it doesn't really matter if they were looking at each other. But what matters a lot is whether they could talk directly to one another. It was a very interesting result. And then they've done a bunch of follow-up experiments where they did more and more of these testing alternative explanations. I actually don't know the current status, but this was one of the first applications of using cross-recurrence analysis to get at something like this. And yeah, kind of interesting that this phasing that appears not to do a lot for the level of synchronization. Okay. So now let's move. So this is continuous, right? So postural sway very often used for synchronization studies, but you could do it with any physiological measure. Like we often do also heart rate. We also have when people are like. You can also, if you have these Wii balance boards, you can put them like on a chair or on a couch, and you can have the people sit on it, and you can also measure kind of pressure. It's not exactly postural sway, but it does give you information also about synchronization. Yeah, but you can have any physiological measure measured simultaneously in two people, or sometimes simultaneous measurements within one person. You can use continuous Cross-RQA to study the synchronization. So this is one of the first applications, I think, for categorical data, and then I already briefly talked about this. This is an analysis of the child's database, I think, which is just a huge collection of natural occurring conversations between children and caregivers, also at different ages. And this can just be, like recordings at the kitchen table or anything. And these are being transcribed, and there's a lot of things known about, they've been categorized in semantic categories and grammatical structures and those kind of things. So it's kind of a data set that is just out there waiting to be analyzed. But very often these are analyzed, of course, in a qualitative manner, and well, Rick Dill and Spivey try to quantify the patterns that are in these data, and they sort of stumbled upon cross-recurrence analysis without knowing that that was actually already an existing technique. Except they, of course, used categorical data. Well, we already looked at like this auto-recurrence of these children's stories, right? So now, if you put two different time series, in this case of conversations, on these different axes. You will also get a non-symmetrical recurrence plot, and of course, when it depends a little bit on what it is you coded about these conversations, but a recurrent point means that at some point you use something, maybe a grammatical structure or maybe a specific word, and if that is repeated by the other person, then this will become a recurrent point. So in terms of conversation, it can mean that exactly the same words are repeated if that is what you put into it. But I think in this case they used the unit of analysis was like the syntactic structure of what was being said. So if you're doing the categorical recurrence, of course you cannot do any embedding. And so I think in COSNET you don't have to worry about this, it's taken care of automatically, but if in some other packages you might want to explicitly say that you're using embedding 1, leg 1, and radius of 0. So one of the things that was actually, I think, really a contribution by these authors is this so-called loss profile or diagonal recurrence profile. And in physics they would call this very different, but here we have a type of analysis you can call leader and follower analysis. Because you can use the recurrence plot or the fact that it's now asymmetrical to decide basically who started something, because these are things that are recurring, right? So in this case it's syntactic patterns, but someone must have, because it's recurring, someone must have used it first, and then someone else is repeating it, because that's why you're seeing these recurrences here. So in a cross-recurrence plot, the 45-degree line that in the auto-recurrence plot will be filled with recurrent points. So the diagonal is not called, no longer called, we call it the line of incidence, but now it's a line of synchronization, which means that if this would be a line in a cross-recurrence plot, it would mean that they would do exactly the same thing at exactly the same time, right? So anything around this hypothetical line of synchronization is pretty close in time. So those are recurrences that occur just one after the other, and as you go further out, there's longer time between the repeating of these patterns. But interestingly, if you think about, so suppose you have a recurring point right here. All right, so this is actually below this line of 45 degrees. So who initiated this behavior and who is repeating it? What do you think? So it's below this line of 45 degrees. So if you remember what you did in the Excel assignment with categorical time series, what you do is you start out here and this has a value here, and you look up and you say, oh yeah, now it's repeating, and you continue and then look up, oh yeah, now it's repeating, So this value here, let me say if I'm saying this correctly, if it's below this line, it means that it is occurring in this time series earlier than in this one. Did I say it correctly? Yeah, so the y-axis is leading the x-axis. And I can show you this in a different way. Suppose you have two sine waves that are just shifted a little bit, or I can shift them a little bit in their phase, basically, just like I showed you with this cross-correlation pattern. We can actually analyze what is going on around this line of synchronization in terms of how many recurrent points we can observe there, right? So you choose like a specific time range. So I'm looking like 100 time points in this direction, 100 time points in this direction, and what I'm going to do is just calculate how many recurrent points are there on this diagonal, how many on that one, how many on that one, and then just plotting this as a kind of distribution. So here we have our line of synchronization. Here we have 100 points under the diagonal. Here we have 100 points above the diagonal. And in this case, we have two noisy sine waves that have exactly the same period. So we see that the number of recurrences neatly align with the period of this sine wave. But here, I've shifted the period of one of them. You can see that the red one here is no longer exactly synchronized with the black one. So here is our line of synchronization. So if they would have a peak in the recurrence points around this line of synchronization, it would mean that they would have been exactly synchronous. But you can see that the peak now is shifted. It's now actually above this diagonal line. And from this you can derive that the sine wave on the y-axis is actually leading, I think, on the black sine wave. So you can use these different patterns that you get, these different distributions around this line of synchronization, to give you a hint about who is leading or who is following the interaction. So in the language development study, they looked at the syntactic structure, and they Oh yeah, this is just one example. This is a figure that they used to explain sort of what they did. And they collapsed a lot of these conversations together. But the way to do sort of the shuffling analysis is, like I told you, you shuffle one of the time series, and in the diagonal profile you then also can report this as a line, let's say, a shuffled baseline. That's what they call it. And so, if you want to talk about peaks in this profile, they would have to succeed the shuffle baseline, because otherwise you can expect that it is a level of recurrence that is could also occur just by chance. So everything above this shuffle baseline we can consider a peak in recurrence, and it tells us something about synchronization. All right, so this would be the plot that they present here, which is actually the global recurrence plot. Someone asked about, can you add these? So this is actually a lot of recurrence plots from different children and caregivers taken together, and they just added. So the gray value is actually a value somewhere between 0 and 1. And then for most children, I think there is. Oh yeah, that's what they did, Jack. So they counted basically the recurrence rates for the different leading behaviors. So more often it was the case that the child would lead the interaction in the conversation than the caregiver. So, but this is from a period in time where they were actually sort of developing these techniques. So they were averaging a lot. And also in the next example, I'll show you that they are I think they never used this setup anymore. So they then went into describing actually individual children and how these patterns of interaction change over the development. Yeah. So do you know these characters? I always have to ask this because it's such a long time ago that our students, they don't know who these people are. Yeah, so that was an early sort of development of ideas for this cross-recurrence analysis, and this is a much more developed experiment, which was published in Psychological Science, also by the same group. So what did they do? Well, they had people come in, a couple of people, to talk about their favorite Friends episode. And they were sitting in front of a screen, which was actually an eye tracker. And they did not record exact coordinates, but they just recorded who are they looking at, and what did they have to do. They had to talk about their favorite Friends episode. And this audio was just recorded. And at the same time, it was recorded who they were looking at while they were talking about their favorite Friends episode. Right, so this could be like Rachel? Oh, who is Rachel? Yeah, I don't know. Anyway, looking at person 1, 2, 2, and then, so you get a time series of who they are looking at while they are talking about their favorite Friends episode. Well, that's not very remarkable, of course, but the actual experiment is then, they brought people in, and they made them listen to these people talking about their favorite Friends episode. Of course, they also were looking at the same display, and then they recorded the movement patterns of who they were looking at while they were listening to someone else talking about their favorite Friends episode. And now you have two time series, one of a listener and one of a speaker. And then the question is, what happens to those eye movement patterns? Are the listeners lagging behind what the speaker is saying, or something else? And so here you have the same idea. You have a listener who is on this axis. You have a speaker who is on this axis. if they would be doing the same thing at the same time, they would be falling on this line of synchronization. But it actually turns out most of the recurrence is occurring below this diagonal line. This is the diagonal recurrence profile, which shows you that the eye movements of the listener are lagging behind, well, pretty long time actually, 2 seconds. So if you want to have the group data, it looks something like this. So this is sort of the average curve for the speakers and the listeners. This would be the shuffled curve. So if you're talking about peaks and those kinds of things, it would have to be above this line. Well, it's well above this line. You see the percent recurrence here. And so on average, you see that these listeners are actually lagging behind in their eye movements of about 2 seconds. So the giver is leading. So this also resulted in some more experiments where they tried to see whether they were able to manipulate this. And there is one way to get this peak exactly at the line of synchronization, which is just bring 2 people in and have them both talk about, they can be in different cubicles, but have them both talk about their favorite episode and allow direct communication. And in those cases, you will see that actually the coupling is occurring at the same point in time. So this is another study just to show you again this principle and sort of the kind of patterns that you can get. This is a similar setup in which you have 2 people. They cannot directly see one another, and also they don't talk directly to one another. They have headphones on, but they talk through a microphone. One of them has a map of the campus, and the other one has a location where she has to go, but she doesn't have a map. And she does have kind of, I think, sort of a Google Map kind of tool in which she can sort of describe without any names or something, but she can describe what she's seeing. And then the other person has to say, oh, you're over there, and then, oh, you have to go there. And they recorded basically everything that these people were doing, so voice, movements, what they were looking at, basically everything. And also video recorded all the movements that they were making, and this was coded in many different ways. And then they also they wanted to know what kind of behaviors, what kind of things are becoming coupled when you ask people to do something like this. And they used also the diagonal profiles from the cross-recurrence analysis. So if you would find something like this, it would mean absolute synchrony. So things are they're doing the same thing at the same point in time. Again, if you find that it's on more on the above the diagonal, it would mean that in this case the follower leads, so this would be on the y-axis, and the other way around, the peak below this diagonal would indicate the opposite. But you can have other things. You can also have a kind of bidirectional alignment where it's not really clear what happens or who initiates it each time. So it can be that it's just sort of kind of a feedback thing that is going on, but it can be consistently consistent through the interaction and a consistent time lag that a particular behavior is recurring. So yeah, well, one of the things that's maybe kind of obvious, but and you would like to have happen at the same point in time is laughing. It would be very odd if you know someone says something funny and then 20 seconds later the other person goes ha ha ha. So this usually occurs at almost the same time. So but this was coded, right? So they had people, many different coding systems, and one of them was when is someone laughing. So that's synchrony. And nodding is it does look a little bit like bidirectional, but this peak is much larger. So this would be sort of more like a confirmation by the follower. But nodding generally is is this response from, okay, now I see this, and then, yeah, okay, and now I'm looking there, yeah, that's okay. This one is interesting, stroking phase. This is occurring at a slower time scale. So if some person starts to stroke their face, then 20 seconds later, the other person will also do, yeah, exactly. And then this will sort of be a bidirectional coupling going on there. Yeah, bidirectional alignment. Okay. Yeah, I have many more examples, but maybe we should stop here now. Yeah, so this is a pretty powerful tool. You can use, again, continuous data, you can use categorical data. You can get actual idea about the synchronization. Yeah.
Maybe I'm just a bit behind. About this diagram that you explained, it means that if stroke phasing happens but the other one probably will do it. It syncs with the other one a few seconds after. So
yeah. Yeah. So if we go back to this.
Yes.
Yeah. So in this case, you have really that there's a very low distribution of recurrent points here. And there's really a peak here. So it's kind of obvious that all the repetitions or all the recurrences are basically due to one person repeating this at a later point in time, right? But in the other one, the sort of bidirectional alignment, this has also a distribution of recurring points here. And so there it's actually not very clear who is leading and who is giving. It's just the only thing you can say is, yeah, someone started it and then the other one repeats it, but then the other one is again. So they're doing, they're flipping back and forth between doing this behavior. And here it's really directed.
But also it means that it doesn't happen exactly at the same time.
No.
It's just,
No, if it would happen at time is 0, then it would happen at exactly the same time. But it's actually not. So it's a delayed repeat of this behavior. Yeah. Okay. No, that's not good. Yeah. So let's see. We are at almost at the end, right? So there were assignments here for Cross-RQA, so you can check them out if you feel like it. But the thing to look for, so this is pointing to to some data that we actually collected during the summer school. So I don't know if you participated. It's people were, you see a circle on the screen and you have to trace with the mouse or with the Wii, I actually don't remember which we used, but you have to trace this circle and so the data here are of this circle tracing. That's a continuous version. But also you might want to look, if you're not interested in doing this analysis, you might want to look at this paper by Coco and Dale. This is actually discussing a different R package to do RQA with, but they have a very neat explanation for all the different aspects, and it's really focused also on cross-recurrence analysis and on these diagonal profiles, so you can get a good description of what is actually meant by that without having to deal with the specifics of the package. Let me see if they have this nice. Isn't that from this one? No. Okay. I thought they had a very nice visualization of the diagonal profile. But as you can see, they really focus on these diagonal profile analyses. So it's a very good starting point if you want to ever would like to use this information. All right. So tomorrow I will talk a little bit about networks, and there won't be a lot of assignments about that, but I can show you some live examples, just like I did with the recurrence analysis, which might be interesting. And then, yeah, you will have had a very nice introduction to all the things that are possible, but of course, probably you are now realizing that it's just the beginning, right? And again, don't be disappointed if you don't fully grasp everything that we talked about here. That really takes some time. It really takes some time to take this different perspective. But I hope that I've shown you some examples that are able to shake you from a statistical inference state and slowly start to move towards the complex systems perspective. So, yeah.
Yeah, so let's say someone wants to think about, for example, recurrence, about the phenomena that they deal with from the perspective of RQA and the measures we get out of RQA, like determinism, linearity, and so forth. Do you have any tips for how to start thinking about the theoretical application? Because this was the thing where they were pointing their finger at the gears,
Yeah.
and so that was pretty impressive in terms of what you draw from theory and then you do that thing. But because you can also just try a million different things and see what comes out. But how to start thinking about, like, put hypothesis in form of like what will the change in linearity be, or what?
Well, that's already, if you're already thinking about it in terms of RQA measures, then you already have an idea that it's possible to do something with RQA, right? So that means that you already have decided that you are collecting time series, probably. So if you're already there, but not a lot of people are already there. Yeah, then it's I think it's always a good idea to look for good examples. Right? So our inspiration was actually this peer system study, but we applied it to intervention efficacy. Right? So that's a big step maybe. But, no, the good thing is that these phenomena, these dynamical phenomena, appear to be rather general. And you just have to figure out a way, how can I observe it? So how can I create a situation in which you can actually observe these things, like critical slowing down, or like critical fluctuations, or those kind of things. And in terms of these coupling and synchrony studies, of course, I think, that's a pretty good idea of this leading, following with the eye movements, and recording something while someone is talking about it. Those are not typically things that you would think about if you're not set on the path of studying how time series synchronize. I mean that's already kind of a theoretical difference. But very often it's possible to, if you're studying change, you're going to run into things like, okay, now the dynamics look different, right? But that takes some time, and you have to be aware of those things and be able to spot them, and then be able to translate them into measurable things. But in general, the first thing I would do is just get inspired by a good example, and then think about how to apply this. Because what these measures mean, especially for RQA, really depends on the situation. So with the stories, high determinism was not good, right? Because you don't want a lot of repetitions. But here in synchronization, if you're expecting synchronization, you expect high determinism, and it's good, right? So depending on the context, you have to, depending on what it is that is recurring, you have to decide what you expect these measures to do.
What about, because we have people from the Faculty of Medicine, so What's your answer when people wonder, like, okay, so can't I just compare cohorts and see which one gets better after I do my intervention?
You mean differences in RQA measures?
No, I mean just.
You want to convince them to use RQA?
Yeah, or
they
take
have
the
to
more
do it, they have to be-
dynamical view.
Yeah. Or what? Or?
To take a more dynamical view, or,
Oh, okay.
or do you think it's okay to just
I
keep
think
on
actually people in
watching
medicine are
cohorts?
not very difficult to convince about. At least I don't have any problems doing that. And a lot of them are already doing complexity stuff. So, well, yeah. If you want to make the case for why it's not interesting to look at randomized controlled trials, it's that it doesn't learn you anything about the process. So if you only want to know if group A who got the medicine and not the placebo is doing better, yeah, then you need a randomized control trial. But if you want to know why, then you need to observe what is going on in this process, right? So you need to observe the process. And that's very often this distinction. So very often if you want to answer why questions about change, you need these techniques. If you just want to establish that a change has occurred, yeah, you need pre-post and then clear, right? But yeah, the question is, what have you learned? If you only know that. It's nice for insurance companies so they can support the particular type of medicine, medication or intervention, but not for science.
See you tomorrow.
Yep.